Welcome to Calculus. Today we will investigate evaluating integrals using the fundamental of theorem of calculus number 1. We'll take a look at 3 examples. As we look at this number 6, the integration from -1 to 2 of the function negative x to the 4th plus 3x squared plus 3 dx, we do want to apply the fundamental theorem of calculus 1. So let's start off by stating what is this FTC. So it is given as an if-then statement, and essentially what we're saying is that if the function, so for us that would be this negative x to the 4th plus 3x squared plus 3, if f of x is continuous from a to b, what a to b will represent for us are the limits of integration. So from a to b, and it's a closed interval. And let's consider that capital F of x is an antiderivative of f of x. Then what we can do is say that the integration from a to b, taking the domain extremes a and b and making them our limits of integration of the original function f of x dx, is essentially the antiderivative f at the upper limit b minus f at the lower limit of a. And that for us is the fundamental theorem of calculus 1. Essentially what it lets us do is find the antiderivative and then substitute in my limits of integration and find the difference. So let's do that now. I want to start off by finding the antiderivative of negative x to the 4th plus 3x squared plus 3. And to help us with that, we just need to have a simple power rule for integrals. So I'm going to write that here in red. The power rule for integrals essentially tells me that if I've got the integration, so this is given as indefinite integration of x to the power of some n value, and that could be a rational number, dx, is going to be equal to x to the power of n plus 1. So take the original function, add 1 to the power, divided by that same x plus, I'm sorry, not x, n plus 1. If I were considering this as indefinite integration, I would put plus c, the constant of integration. So we just need to apply power rules for integrals to find the antiderivative, and then what we'll do is we'll apply the fundamental theorem of calculus to evaluate the definite integral. So let's start off with our antiderivative here. So again, I'm just going to apply this power rule for integrals one term at a time. So the first one here is going to be negative. So I need to add 1 to the power. So it's going to be x to the power of 4 plus 1 or 5. And then divide by that same power plus 1. Okay, we'll move to our second term. So plus 3. Do just put the constant. I was treating that negative like a -1 constant. So 3 is a constant. And then for x squared, we could apply the power rule or our property for integrating the quadratic parent. So it is x to the power of 2 plus 1, 3 over 3. And then lastly, for my linear term, that's x to the power of 0 is the variable term kind of hidden or suppressed. It's going to become an integration 3 times x to the power of 0 plus 1 over 1 over 1. So there's my antiderivative. Now I do want to integrate this from -1 to 2. So as I simplify this, I'm ultimately going to substitute these limits into this antiderivative, but let's simplify it first. So I'll write this as negative x to the 5th over 5. My 3's on the second term will cancel, so that's just going to be plus x cubed And for my third term, simply plus 3x. So that's my simplified antiderivative. And again, we're going to evaluate now using the fundamental theorem of calculus 1 from -1 to 2. So we'll set that up using FTC1 here. So I'm going to start off my f at b, capital F at b, is really taking my antiderivative and substituting the upper limit of integration there. So that's going to become -2 to the power of 5 over 5 plus 2 cubed plus 3 times 2. I'll put that all as one expression minus, so remember the fundamental theorem of calculus gives us the difference, so minus my second substitution now is going to be with the lower limit of integration, so -1 to the power of 5 over 5 plus -1 to the power of 3 plus 3 times -1. Now for me to evaluate that integral is just to simplify that statement. So what I see from my next term is that I really just want to combine these pieces here. So this is going to become -2 to the 5th is 32 over 5. And then I got 2 cubed is 8 plus 5. And that's going to give me 8 plus 5 is going to be 13. But I want to represent that as something over 5 so that I can combine those. So 13 times 5 is going to be 65. And when I combine those two, 65 minus 32 is going to give me, I see I made an error here in the 65. 2 cubed is 8, but 3 times 2 is going to be 6. 8 plus 6 is 14. So I should change that numerator. 14 times 5 is going to be 70. So got to watch on the arithmetic with this because it does involve a lot of calculations. That's going to combine as 38 over 5. Okay, let's simplify the second expression here, which is the antiderivative with the lower limit -1 substituted in. So again, we just want to take that piece by piece. This first fraction, -1 to the 5th, is really going to be -1 still. That's an odd power, so it preserves the negative, but then -1 times the negative that's already there is going to be +1 over 5. This -1 cubed is going to be -1, and then 3 times -1 is -3, so that's going to be -4. But again, I want to call it something over 5, so -4 times 5 is -20. And ultimately, I'm going to have 38 over 5 minus -19 over 5. And that's going to turn to plus because I got the double negative. So ultimately, 38 over 5 plus 19 over 5 is going to give me really a chance to add my numerators. And that's going to be 40, 57. +57 over 5. Let's take a look at a second example that involves a power of x that's in the denominator. So here's number 11, the integration from -3 to -2 of 4 over x cubed dx. What I'll do for this one initially is just convert that to, from having x cubed in the denominator, bumping it up to the numerator. So I'm just going to call this the integration from -3 to -2 of 4x to the power of -3. Remember, that power just becomes negative as it moves in the fraction dx. So then I can apply my power rule for integrals. Again, it says I've got the integration of x to the power of n dx. That's equivalent to x to the power of n plus 1, excuse me, over n plus 1. And then in the indefinite form plus c. For us, we're calculating the definite integral. So let's apply that here. Let's find the antiderivative. So it's going to be that coefficient 4 times, so I got to add 1 to the power of negative 3. So that'll be x to the power of negative 2 over negative 2. And then this is just one term, so it's a little simpler. I'm just going to evaluate this from negative 3 to 2. We want to clean up and simplify that antiderivative. So 4 divided by negative 2 is going to be negative 2. And then I can let that power of x descend so that it is a positive power. So that's over x squared. And we're going to evaluate that from negative 3 to negative 2. So again, let's simplify that. I'll apply the fundamental theorem of calculus 1. So my first term, I'm going to substitute in the upper limit, excuse me. So negative 2 over negative 2 squared. And I'm going to subtract. So remember, fundamental theorem of calculus is f at b minus f at a. So my f at a is going to be negative 2 over negative 3 squared. So that's my numerical representation. I just need to simplify that. So that's going to be negative 2 over 4 minus negative 2 over 9, which ultimately is going to reduce down to negative half plus 2 over 9. So I can probably just easily create like denominators here. Multiply the 9 on the first fraction, multiply the second fraction by 2. And what that will give us is now negative 9 over 18 plus 4 over 18. And if I combine my numerators, now that my denominators are the same, negative 9 plus 4, negative 5 over 18. So one thing we see with fundamental theorem of calculus is it speeds the process of definite integration up. Well, let's finalize with a last example with a fraction power. Here I've got, in number 13, the integration from negative 7 to negative 6 of x to the power of 1/3 dx. So we'll apply our power rule for integrals first to help us find the antiderivative of x to the power of 1/3. So again, it's going to be x to the power of 1/3 plus 1, so that's to the power of 4/3. And we'll divide by that same power. And we're evaluating this from negative 7 to negative 6. Again, I want to clean that up, simplify the antiderivative there. That's going to be the reciprocal of 4/3. Since we're dividing by 4/3, we can consider that as multiplying by 3/4 times, I'm going to convert x to the power of 4/3 to a radical expression. So remember, the root is the denominator, so my denominator is the 3, so it's the cube root of x to the power of the numerator power of 4. We'll simplify easier using that setup. So again, I want to integrate that antiderivative from negative 7 to negative 6. Now let's apply the fundamental theorem of calculus to find that value. So I've got 3/4 as a coefficient. So what I'll do first is I'm going to substitute in the upper limit of integration, negative 6. So that's going to be times the cube root of negative 6 to the power of 4. And then I'm going to subtract minus, again, 3/4 times the cube root. And I'm going to substitute in now the lower limit of integration, -7 to the power of 4. So that's substituted in. Now I need to just simplify that response. So that's going to be 3/4. This is equivalent, if I think about that even power of 4 within the cube root, it's equivalent to +6. That's going to make it all positive. So the way I'm going to group this, I will make it +6, but I do want to group it as 1 power of 6 and 3 powers of 6. Do the same with the 7. So again, because it's a power that's even, it's the 4th power within the radical, that's equivalent to +7 to the power of 4. So I'll write this as the cube root of +7 to the power of 1 times +7 to the power of 3. And my reasoning for grouping these this way is now I can extract part of this value inside the radical. The cube root of something cubed is that number. So the way I'm going to finalize simplification here, this is going to be 3/4. In fact, I'll write it as 1 fraction since I got common denominators of 4. This 6 cubed is going to exit the radical as simply 6. And we're going to leave the cube root of the lone power of 6 there, minus 3 times this 7 to the power of 3, the cube root of it is going to be just 7, times the cube root of the lone power of 7 that was still there. And ultimately, we're going to get this reduction. It'll be 18 times the cube root of 6 minus 21 times the cube root of 7 over 4. We can get a decimal approximation for that using the graphing calculator. So I'm going to just head over to Desmos. And let's type it in as we just did in a fraction form. So it's 18 times the cube root of 6 minus 21 times the cube root of 7 over 4. And that's going to give us an approximation of -1.866 if I take it to the thousandth. And we'll just take that back to the note screen to finalize that answer. Has about the value of -1.866. So thank you for joining for this investigation of evaluating definite integrals using the fundamental theorem of calculus 1. See you soon.